James Nugent. I'm a developer from London, England originally, and now New York and Austin, depending on which day. I work for a company called Boundary, which builds monitoring software that gets used. It's a software as a service monitoring product that gets used in a lot of different places and does network flow monitoring and that kind of thing. So that's the last slide we're going to see during this talk, because the best way of learning any programming language is to write some code. So out of interest, who here is a .NET developer primarily? Cool. And JavaScript or something that's not .NET primarily? Okay, cool. So who's heard of Go before? And who's tried playing around with it? Okay, so that's a reasonable mix. So I have more content probably than I can get through in an hour. And I'm just going to go through it in a list in an order that seems logically important to give you a brief introduction to the language and the standard libraries that come with it. If there's something that you want to hear about in particular instead of what I'm talking about, then just interrupt and shout, and we'll look at that instead, assuming I know what it is. So let's get started. So the traditional thing with any programming language is hello world, and this is no exception. So we'll write a quick hello world program in Go. And so Go code goes in files with the .go extension, unsurprisingly. Is the text size okay for everybody, or does it need to be bigger? Okay, cool. So I'm just going to use Vim. You can use any editor for writing Go. Yeah, I think even Visual Studio Code supports it if you're on something that runs that. So the entry point, so similar to the way that if you're in .NET, you have a public static void main with string array of arguments. The entry point to a Go application is a function called main. And it can take arguments if you need to, but we don't need any at the moment, so we'll just leave them off. And to do a hello world, we're going to need to be able to print to a console, because this is just going to be a console application. And the part of the standard library we use for doing that is a library called format. So we can use format.println in this case. And we'll put in hello world, and that's the entire program. Now, when I save this, the editor's going to do some stuff in the background to put in some parts that I missed out. In particular, it's going to put in this package declaration, which is main, which is part of the entry point of any application. So the main function when you start the program is in a package called main, and the function is called main as well. And the second thing it's going to do is fill in my import statement for me. Now, Go is kind of fiddly about import statements. It doesn't allow you to have unused import statements and have valid code that compiles. And it obviously won't compile if you're using code that's missing an import either. But the tools will, for the most part, go and work out what you meant and go and correct it for you. So if I took out this import again and then saved, it would realize that I'm using a function from the format package, and it will import that format package for us. So let's write that file and quit. We'll notice it's built it in the background for me, but we'll remove that and see how to build it properly. Now, Go is a statically linked language. That means the only dependency it has is on libc in some cases, but for the most part, it has no dependencies at all. However, it's architecture and operating system specific. So unlike Java and C# or .NET, you can't compile a program on for one platform and have it run using the runtime on another platform. So with .NET, you could take your Visual Studio on Windows compiled .exe file and run it on Mono under Linux, for the most part. The advantage of this is that you don't have to deploy anything on your server beyond the executable file. In fact, as of now, the stable versions of Go can't even load shared libraries. Everything has to be statically loaded in. That's not true of the version that's coming out in a few weeks' time, but for now, that's true. Luckily, we can cross-compile, so nobody wants to have like 6 build systems up just to build for different operating systems. That's kind of a mess. But the Go compiler is good enough that you can build for every operating system it supports from any other operating system it supports. So I have, in this case, if I just do Go build, then I'll end up with a file which is a Muck executable for 64-bit. So that's a Mac OS application. There's a whole ton of other compilers installed. If I type Go and then tab, it will show me all the different compilers that are installed. So there's ones here for Linux, Windows, BSD. There's various ones that will compile for everything in one hit and produce you separate files for every one. In this case, if we just do Go Windows AMD 64 build, then we'll end up with a hello world.exe instead. And if we do file hello world.exe, just to see what it thinks it's a 64-bit executable for Windows. And if we copy that over to a Windows desktop briefly, which I have here, you can just copy that in there and cd desktop. No, that one. How do you clear it? And then we do hello world.exe. Then we get a program that actually runs on Windows. If we tried to do that with one of the Unix ones, then it would obviously fail because it's a bad image format. So that's, I'm not going to do any more with Windows. But you can cross-compile very easily, and all the standard library functions work across every operating system, with the exception of some system calls, but you don't need to use them very frequently. There's another interesting area of Go which I don't really like, which is the project organization system. It forces a view upon you of where you store your code, where it builds, the layout of the paths that you use. So if you look at the path that we're in when we edited that hello world.go file, there's this thing called a Go path. Now a Go path has 3 top-level directories in it: bin, source, and package. And the Go tool will use this thing to resolve imports and things like that, because you can import other people's packages in exactly the same way as your own. You don't have to go around adding references to DLLs and that kind of thing. The corollary of that is that every dependency has to be a source dependency because there's no way of linking to libraries. So if you look inside source, then the convention is different source code hosting repositories are in the top level. So we have code.google.com, github.com, golang.org. And then within them, you have the different usernames within that, not sure what happened there. Within that repository, so in my case, we have JN20 on GitHub. And then you have the actual project. So you can refer to a package that's in a different library with the entire path to that package, and it will resolve it for you. So you could import, hot corners, not a good idea. You can import this github.com/jn20/hello world, and that will count as a library, and it will resolve where it is at build time. I personally don't like that system because it tends to commingle code together that doesn't really need to live together. One way of getting around it is there's an environment variable which you have to set called gopath, which I've just got set to code/code-on-the-beach/gopath at the moment. You can set this for every project, and then you'll get a clean working directory for every different project. There are various other tools besides the Go tool which will do that for you. So that covers most of the weird things about the setup. It's a fairly straightforward, one binary download. It's about 4 megabytes, maybe a bit more now, but not very much more. The other thing that's worth looking at is the documentation, because the documentation is actually good. If we look at, for example, the format.println, I'm using a documentation browser here called Dash, but you can get it from the command line with go doc format println, and it will just give you the description of that. Or you can, in general, if you Google Go and then the function name, you'll get the Go doc back up as the first thing. This is all written in line similar to the XML documentation in .NET, or in C#. I'm not sure how you do it in F# offhand. But what we can see here is some interesting things. So we have a variadic function which is the same as most print formatting or print line functions, where it'll take as many different arguments as you want and concatenate them together. But it returns 2 things. So every function in Go can return more than one value. And there are no exceptions. So everything either returns an error, if it's possible that it can throw an error or cause an error, and normally some other results as well. So in this case, we get 2 things. We get the number of bytes that we wrote to whatever we're writing to, and we also get any error that was encountered. So the traditional patterning Go for error handling is a bit different to most modern languages, with the exception of C, I guess, which have exceptions. So let's look at something more interesting than hello world. Let's look at an HTTP server. So there's HTTP support built into the standard library, so writing web services, web servers, and things that return JSON over HTTP or XML over HTTP or whatever over HTTP are pretty straightforward to write, and you don't need to take any third-party dependencies. So if we look at main.go here, this is a bit longer this time, and we can see a few different things. Go doesn't have classes in a similar way to F# for the most part. If you're writing idiomatic F#, then you don't tend to use classes. You tend to use data structures and then functions which operate on those data structures. So Go has a way that you can attach functions to structures, but there's no class support, so you can't encapsulate things in the same way as you can with an object-oriented language. So you can get some of the way to object orientation, but not really all of the way with it, which may be a good thing or a bad thing depending on which way you look at it. Probably depending on what you're trying to write as well. So let's look at the entry point for our HTTP server. We've got the HTTP package, and there's two functions in here, handle func and then listen and serve. So if we go look at the documentation for these, HTTP handle func. So handle func registers the handler function for the given pattern in the default serve mux. Okay, so that's not that helpful. So let's think about what an HTTP server is. At some point, someone's going to open a TCP socket to a given port and send an HTTP request, which is going to look something along the lines of HTTP 1.1 get some page name, or get default page name, slash or whatever. To be able to work out what's going to respond, you need something at the other end listening, realizing that it's HTTP firstly, so that's the server part implementing the protocol, and then something which will do routing for you. So it will take the path component of the request and work out where it's going. And the thing that Go uses to do that is called a serve mux, which I guess is short for a serve multiplexer, because it allows you to put several different paths on one server. And what we do here is set for the slash, or for the root URI, we're going to say when we get the root URI, we want to use this function hello to process that. So as soon as we get a request made to slash, we're going to start executing this function, which is called hello. You can see the function declaration means that we take in two things. We take in a response writer and a request, and we don't return anything. The second part of the main function just sets up, so we do listen and serve, and that sets up the port that we're going to use, and in this case, we're going to bind to every IP address on the system. So let's run this and see what it actually does. Where are we? Simple HTTP server. And it seems to be running, so if we curl localhost 8000, then we get some JSON back. How did that work? And we wrote 60 bytes to the client according to the log. So how did we do that? The request is going to have the standard sorts of things that you'd expect to see on any framework that's processing HTTP requests, because the standard defines for the most part what's going to be on them. And we can use those values, and then we can write to the response writer. And in this case, we have three things we can write. We can either write a header, we can write some data, or we can write... OK, so we can set some headers. We can then flush the headers to the client, and then we can write data. There are ways of doing multi-part responses as well. So what does this show us about the syntax? The first thing we've done is set up a structure. So a structure is it's a bit like a class that has no behavior associated with it. It's just public data fields, similar to a type in F#, I guess. Record type, that's the one. And in this case, we have two different fields on it. One of them is called name, and one of them is called date. So you'll notice there's no private or public keywords here. Go uses a slightly weird convention which I'm not sure if I like or not, where capitalized things are public and lowercase things are not public. Right? Kind of weird. So in this case, this function hello is not public because it starts with a lowercase letter. If we were to change the type of this to begin with a capital G, then that will be public. And by public, this is from the package rather than from a class because there's no concept of classes. So we have a structure with two fields, and we can initialize that with a syntax that looks fairly familiar to, it's kind of similar to the uniform initialization in C++ or the constructor arguments initialization in C#. I think you can do the new and then open brackets and then fill in the fields. And in this case, we're just filling in some nonsense values. So one of the things the standard library has is a JSON library, which is quite reasonable as far as I'm aware. I don't think it's slow. JSON.decoder or JSON.encoder. If we go to the top of this package, then we'll see there's a function here called Marshal, which will take an object and give us back JSON for it. So that's what we're using here. We're taking this structure which we just initialized, G, and we're passing it into the Marshal function. And that's going to give us two things back. It's going to give us the result as a byte array so that we can write it down to the client. And it's also going to give us potentially an error. So this explains the error handling pattern that's very commonly seen. It's very common that you see a function call, and then you see a check to see whether there was an error or not. And the convention is if there's no error, things return nil, which is the Go equivalent of null. So it's very common to see these blocks of if error is not equal to nil, then do something with it. In this case, we don't really have anything sensible we can do beyond close the socket and log a message saying that we couldn't do anything because we don't want to block other clients just because one had an error. And we should probably actually return there as well. And that will just close the client socket and have done with it. You can see this pattern everywhere. It also brings up a few other elements of the syntax. So there are no unnecessary brackets. Everything is just, that's a syntax error effectively. Everything just gets done without the brackets. But the curly braces are mandatory. So you can't omit them like you can in most C-derived languages. That's also a syntax error. We don't have any loops in here, but now's a good time to mention the looping syntax, just while we were talking about the curly braces and no brackets. There are three types of loop. There's the loop which does, there's the standard loop, which is, for I equals 0, I less than 10, I plus plus, and that will just give you a 1 to 10 iteration. There's a second type of for loop, which is the equivalent of a while loop, where you just put the condition up here. And then there's one which will just loop forever, which you write like this. So this is the equivalent of doing while true in C#. That can be useful for servers or where you know you're going to break out based on some condition. There really aren't many different syntactical elements to Go. It's a fairly simple language that's been designed to minimize the number of different things that you have to learn about. One of the things you do have to learn about, though, is variable creation and declaration. So sometimes up here, actually I think in every case here we've used this colon equals as the assignment operator. Now the assignment operator is interesting. Personally, I think it's a mistake because it means that things that are the same don't look the same, and things that look the same aren't always the same, which is normally a bad idea in a programming language. So there are two different types of assignment. We could either create a new variable and assign a value in one go. So we could do test equals string, for example. That's perfectly valid. It will tell us that we have an unused variable, but it's still valid as a declaration. Once we've declared it in that way, though, we could also reassign it using the single equals without a colon. We could use world there instead. And that's valid, but this is not valid because we haven't got test declared anywhere. So the first time you use a variable, you end up using the colon equals to declare it effectively. There is another way around that. If you prefer explicit declarations, then you can do var test and then define which type it is. And then the error about the declared variable that never gets used moves up to the declaration. But the assignments are all valid. So you end up using colon equals to declare a new variable in the most part. Most idiomatic Go code uses that colon equals syntax. So let's look at, okay, JSON writing is a fairly common thing that people end up doing with when they're writing a web server, right? You end up with some structure that you want to represent as JSON to the client. As a side effect of public fields or public structure members needing to start with a capital letter, by default, that means that our JSON, when we write to the client, is going to end up with capital letters in all the names. And all the JavaScript programmers probably hate that because the idiomatic thing in JavaScript is to use camel case with a lowercase starting word. So let's look at how we can change that. So fields on structures can kind of have tags on them. So these kind of equate to attributes on class members in C#. So you can put like a square bracket over the top of a member and put something like, I don't know, data member or serializable or something like that in there. Go has tags for that. So we write tags with a pair of backticks. And then you can chain the tags next to each other. So in this case, we're going to use one for JSON, and we'll say name. And in this case, we'll say JSON, I don't know, we'll give it a different name to the value rather than just changing the case, so we'll say start date or something like that. And then when we write that, it will reformat it. And if we restart the program and make another request, this time we'll see that the fields, well, I don't know, we could probably, sorry, into JQ dot. Then we could format it instead, and we'll see that we get the values that we defined as the field names. There are various other things you can do as well. So we could change the format of the date, for example, which is not that pretty at the moment. And these will go arbitrary levels deep. So we could go and change our code to nest another structure. So if we define, I don't know, type name struct, and then we do first name, last name, and then we'll change name rather than being a string that it will be a name instead. And that will change our initialization because that's no longer a valid structure for that. So we can put in there a name where first name is James, last name Nugent. And the thing to watch out for there is that the trailing commas are mandatory. I'm not sure if field and value initializers. Oh, that's because I need to specify the field that that's going in. So the trailing commas are all mandatory. So you can do that in C# and I believe F# as well. The good reason for doing it is that only the lines that actually change if you go and add another one. So if you think about looking at a git diff for someone who's added something to the end of a list, you always end up with the previous line being changed to add a comma, and then the actual changed line underneath it. So this kind of avoids that. I don't know whether that's the reason they did it, but that's a nice side effect of it. So if we run this now, we can end up with, we'll end up with our structure being slightly different. And we'll end up with we didn't tag any of the fields, so they've got their default uppercase names representing the field names. But we've got our structure here. So this can go arbitrarily deep, and it's pretty straightforward to change it to XML instead. Or I think there's various weird and wonderful formats in there. I think you can use ASM1 if you particularly wanted to, or encoding. So there we go, the CSV. Some of these you can't do automatically, but all of them have support in the base library. What should we look at now? So is everybody following along so far, or is anything unclear? Okay, cool. Is there anything in particular that people want to look at, or should I just keep going through the stuff that I've got going? Okay. Let's look at how we use an external library. So, which library are we going to use? We could use, okay, so there's no built-in UUID type. So a UUID, or a GUID as Microsoft calls it, is a 128-bit number, which you can use for unique identification. And there's various well-known methods of generating these things such that they're likely to be unique within the universe. There's a package for this, though, which implements UUIDs and the generation of them, although I'm not quite sure why it's not in the language, but it's not. So we just have to deal with that. So to download a library, there's no equivalent of a package manager as such for Go, but there's a command we can use to go and get a library if we know its URL. So we can use go get and then the package name. And that will go and download it, and it will put it into code.google.com p. So this is that's that part of the URL, and then go UUID, and then we end up with the actual package. So if we go into UUID, that's where the actual Go files are that implement this method, that package. So let's go and put one of those on our. Actually, I can use CG Gen20 simple HTTP server. Let's go and put one of those on our response for a second, just so we can see how to import and use that. So we could set up the import ahead of time by just pasting in the path to the code. So that will resolve it via the Go path that we just talked about, and import the package called UUID. Unfortunately, if we save at this point, as is natural to do, then the tools will realize that we're not using that at the moment, and it will take it away again, which is a source of a lot of frustration a lot of the time. But we can paste it back in and then go and use it without saving, and it won't be too bad. Maybe. Okay. So maybe we'll just put a UUID on every response, just so that we have some way of correlating them. And we'll call it ID. So the way you refer to structures or types within a package is to use the last part of the package name that they import by default. And that will give you all the types within it. So in this case, we have various different constants we could use, various different functions we can use, but we're really interested in the types. And in this case, we're interested in the type UUID, which represents a GUID. And we'll say the JSON is going to say message ID. So that's fine. And now we'll notice that the formatting tool by default separates out third-party packages from standard library packages with a new line. The convention, I think, is that you have the standard library packages, then your own packages if you have any. So if you're building a modular system, and then you have the third-party libraries that you use. And in this case, we can just say ID, and then there'll be a function somewhere in UUID's package, which creates us a new UUID. And in this case, it looks like it's called new UUID. So that's all good. New UUID. And that's a function which takes no parameters and just gives us back a UUID, which is what we'd expect. So now if we go run this again. Oh. That didn't work. Oh, go build. I think we've still got it running somewhere. Yep, there it is. So the port wasn't available to use. And then we can go and make another request, and we'll see that we get a UUID in here now. If we go look at the syntax for that, it brings up some interesting not main, vim main.go. It brings up some interesting other areas. So we have this UUID here, if we go and look at what that actually is underneath, so we can go to its definition, and it will go to the source that Google wrote for this. And we can see that it's a type UUID, so that's the name of it, is a byte array. Except this isn't really an array because it doesn't tell you how big it is. So arrays in Go there's two different concepts for arrays. The first is an array which is a given type, given size, and the type equivalent is only between arrays of that size. So you could have an array of 5 elements, of 5 ints, and the only type that's equivalent to that is another array of 5 ints. An array of 6 is a different type. The other thing you can have is a slice, which is what this is defined, which says this is a sequence of bytes which will be stored together in memory, but we don't know how big it's going to be at the moment. And those are equivalent between things of the same type. So in this case, all byte slices, you can pass one in wherever you need to pass another one in. Let's look at that for a minute with ints instead. We'll just make a new project here called slices. And put in a main function. Println hello world, just to get the imports in and make sure everything's working. Cool. So let's define here an array of integers, or a slice of integers, and see what we can do with it. So we have we'll just do numbers equals, so we'll declare the variable numbers, make, and then slice of int, and we'll say it's going to be 10 long. So this is a built-in construct. So this looks like a function call, but it's actually a part of the language. So make can be used for building, for constructing all the built-in types. So you can use it for constructing slices, and you can use it for constructing channels, which we'll hopefully get to shortly. And also arrays and a few other things as well. So what this is going to have given us is a 10 slot array. And then numbers, sorry, a 10 slot slice, and numbers is going to refer to that. So we can do most of the usual things that we'd expect to be able to do. So we could do for I equals 0, I less than 10, I plus plus, and then we'll say numbers I equals I. Pretty straightforward array, and then maybe we'll have another one. We'll just copy that, and we'll go and print them all out afterwards. So we'll say format.print I, and then space. I think that works. So if we run that, then we just get the numbers that we expect, 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is where it becomes more interesting. There's no concept of generics in Go. I suspect at some point they'll get added, but right now you end up writing a lot of boilerplate code that generics can get around. So there's no equivalent, there's no built-in standardized way of doing a map or a filter, for example, because there's no generic way of referring to the types. If you're interested in a language which is kind of like Go, as in that it's statically linked and that it's focused on speed of development, that kind of thing, then, but you also want generics, then Rust is a very good choice. I suspect Swift will become a very good choice when Apple open source it to run on something useful on the server like Linux, which is apparently happening in November. That might be a good language. It also looks a lot like F#, so if you know F#, then Swift is a very good language to pick up because it's designed by much of the same team as I understand it, so it's kind of similar. So let's go back to this. We had this make slice of int. Quite often, though, what you want to do when you're doing systems programming in particular is pass around references to sections of a bigger array. So maybe you've read in a client request off a network, and you want to pass around certain parts of that to be processed, but you don't want to copy them all the time. So in C# or in .NET, rather, you'd use the class called array segment, which I think I have the .NET documents up here. Array segment. Okay, I don't have the .NET documentation. Oh, okay. There we go. So we have a generic array segment of T, which represents an underlying byte array, and then two numbers through it, which are where do you want to start your slice of it, and where do you want to, and how many bytes do you want, for example. It's normally an array segment of bytes, but you can use it on any array. So the equivalent of this in Go without, it has this built in as a native concept, because you can, we called this thing a slice rather than an array, and we can keep slicing it and pass those references around. So we could here, for example, say low numbers equals numbers, which is the base array that we want to use. And then we'll say we're going to take 0 to 5. And then we'll just go and print numbers, low numbers instead. Oh, that's the reason that did that. Sorry. Turned out to be the same result, but the code was wrong. Numbers I. Low numbers I. Now what we don't know is what size we're going to get passed around here. So instead of hard coding that in here, we can use the length function instead. So there's a built-in construct similar to length, which will tell you, similar to make, in terms of its place within the language, that will tell you the length of various things. So in this case, we can use length of numbers, or len of numbers. Or here we could use len of low numbers, and that will give you the size at runtime. So if we run this now, we'd expect to see 0 through 5, or 0 through 4, sorry. Maybe we'll put in a few line breaks here. So the first time round we got 0 through 10, 0 through 9, which we'd expect, and the second time round we got 0 through 4, which is because we sliced this thing to start at 0, and 0 inclusive, or element 0 inclusive, and go up to element 5 exclusive. So that will give you a slice of size 5, which contains 0, 1, 2, 3, 4. If we go and fill this slightly differently, maybe the numbers are a bit less, maybe if we do I times 10, that will give us more readable results. So we end up with 0 through 5 in the array, and then 0 through 10 in the original slice. You can also do different ranges with this, so you could say maybe I don't want to get the first one, but I want to get all the others. So you can omit one of these and say we'll start at 1 and go through the end of the array, and that way you don't have to know the length. And you could also do that with len of numbers minus 1 and that kind of thing, but there's built-in syntax for that, so we don't have to. So if we run that, we'd expect to see the second. We'd expect to skip the first one and then get all the rest. This is kind of flexible because you can use this on any slice type, and it's quite idiomatic to see it used fairly heavily in Go code, especially when you're dealing with lower level stuff. But for example, it's more common to pass around byte arrays than it is strings in some cases, especially when you're reading to and writing from network interfaces. That leads us to an interesting question, though, of how do we type convert between these things. So earlier on when we did it, we used a JSON marshaller which took in a structure and produced us a byte array. But what if we just have a string that is some JSON and we want to get a byte array out of that? So that's also fairly straightforward. We'll get rid of numbers for a minute and keep our printing code. And we'll say string form equals, let's just put in some, hello. Have to think about how to write JSON now. Is that valid JSON? Yeah, it looks valid. So let's get a byte array out of that so that we can send it down the wire, because most of the writing functions, if we look at the interface that most writing things use, they all take byte arrays rather than strings or any other types. And there's no way of overloading functions, so it can't do the thing that the I/O streams do in .NET, where you can send any type down and it will do the coercion for you. So in this case, we could just say bytes form equals string form dot byte. Or sorry, the specifier goes first, I think. What's wrong with that? Oh, okay, so that's a nice error message to look at. So it says invalid type assertion string.form as byte, so we can't do that. Actually, there's another method we can use, which is you wrap it and call it as a function, like that. Some things you can convert using the casting syntax of dot and then whatever. Some you can't. That's also used for casting down a type hierarchy, which is actually valid. And then if we look at bytes form here instead, and then we get rid of all this other code, we should see that we end up with the bytes of our JSON represented as decimals. So in this case, we'll just see probably ASCII, because nothing goes high enough to get out of the standard ASCII range. Let's look at a more interesting example. Who's come across event sourcing before? Cool. Okay, so the idea of event sourcing is, at high level, is that you capture the state changes of objects as a series of events that describe what happened to them. And there's a nice idiomatic way of doing this in Go. Events, it turns out, map very naturally to the structures. So events, for the most part, are just data bags, right? They have a name which describes what happened, and they have some properties that describe how it happened. And in some cases, they don't have any properties. So in the case of this, we're looking at some fictional airline system here where we record flights that were taken, we record status matches that occur, we record when somebody was promoted, and we record when an account was created. So those are the events in our system, if you like. So the way of doing this in most languages, so if we think about how we'd implement it in, say, F#, are there many F# developers here? Cool. So if you think about how you'd implement event sourcing in F#, you'd do a fold, and you'd do a pattern match on the event type, and then you'd have your state as a record, probably, and then you'd return a new state every time you apply an event on the pattern match. So in C#, the normal way of doing that is to have an object which has its state and then has methods on it which will take each type of event and describe the state change that occurs, and you'll mutate the fields within the object. So Go although Go isn't object-oriented, you could do it that way, and you can try that, or you can also use a very nice bit of syntax called type assertions, which we kind of just happened against them when I got the syntax wrong for conversion. What we're trying to implement, the functional pattern that we're trying to implement, is called a left fold. So that takes in some seed value, and then you apply, you pass the result of one calculation into the next. So you end up with a chain where every calculation returns a new intermediate step which goes in with the next one. So for example, if you were going to fold numbers, then we'd have, I don't know, if we're going to fold 1, 2, 3, 4, then we have to take some seed to start the fold, so we'll take 0 in this case, and then we'll take our function as being plus. So in this case, we're going to start with 0, and we're going to say, so 0 plus 1 is obviously 1, and then we're going to take that as the feed into the next part of it. So we're going to take the 1 that was the result of these two and use it as the seed for this one. So in this case, it's going to be 1 plus 2, so we're going to get 3, and then in this case, we're going to use the 3 for the next one, so we'll end up with 6, and so forth. Now you can do this with any types, though, provided you've got a function which operates on them. So in this case, what we have is our definition of the state. So we have our frequent flyer account, which is here. We're just going to define it as a structure which has the different bits of state that we're going to need. So in this case, we're going to have an ID. We're going to have the number of miles that somebody has, the number of tier points that somebody has, and then status. So status is just a series of constants represented as integers. There's no nice way of doing enumerations really in Go. There's a good way of overriding to string. So the equivalent of doing override to string on a CLR object is that you implement this interface called stringer. The convention in Go is that every interface is active. So it's a stringer, it's a writer, reader, which sometimes comes up with very unnatural English, such as stringer, but never mind. You can tell normally when you see an ER on the end of a word, this is an interface that's being implemented rather than something that actually exists in its own right. You can just take this thing, it will take an object, and it will return the string. So in this case, we can go and implement our fold using type assertion. So what we're going to get, there's no way of doing an object hierarchy because you can't inherit one structure from another. So the best we can do is take anything. So this is the equivalent of saying we're going to take an array of objects where we don't know anything about the type inside them. This interface construct is everything matches this. It's the equivalent of object, except it's not really an inheritance hierarchy. All it says is everything can respond to nothing, so you can use interface to refer to anything. And in this case, we have a slice of them, and it's called events. So if you think about how we do this in F# or in functional C#, we'd take in an enumerable of events, and we'd go through them one at a time, and we'd look at the type, and we'd match based on the type, and we'd do some action according to the type. That's how we'd implement the fold, right? So in this case, what we can do is go over every event. So range is another one of these built-in keywords that will iterate over every element in a slice or in an array, and give you each one in turn. And it will give you two values for it, actually. It will give you the index, and it will give you the actual value. Now, we don't care about the index, so the conventional way of getting the compiler not to complain about unused variables is to use an underscore as a name for a value that you don't care about. That's fairly commonplace in many functional languages as well. So what we're doing here is saying we're going to go over every event that we've got in our history, so in our event source history, and we're going to look at the type. So we're going to do a switch, so a pattern match. It's not really a pattern match, except on the type. It's kind of a poor pattern match, but it's a slightly better switch than C# has for the most part. And we're going to go through and look for the individual cases to match. So we have each of our 4 types of event here. We have the frequent flyer account created, we have the status matched, we have flight taken and promoted to gold status. And we can use that type assertion, which we accidentally fell across a minute ago, to make E refer to whichever one of these matches. So if we're in this block, then E is going to be of type frequent flyer account created. So we can use all the fields there, and the tooling will actually complete them for us. Similarly here, if we're in this one, then E will be a flight taken. And we can, and that's the case with all of those, and we can just return a new state every time. That's actually a pretty nice implementation of event sourcing. It's not generic, because it's obviously coupled to the types that we're using here, to the event types. But for the most part, it's pretty straightforward, and you can see exactly where you'd have to go and debug one of these things. So if something's being applied incorrectly in when a flight's taken, then it's fairly obvious where you'd have to go to fix that. And it's kind of nice that everything stays together. So there's one other area which is worth a bit of investigation. Does anybody have anything else in particular they want to look at?
What's the debugging experience, and is there any way to, I'll let you do that one first.
Okay. The short answer is no. The debuggers are all terrible. So you can debug using GDB. It's not very good. There are various new debuggers which are starting to come around now, which are improved. I've honestly not tried any of them, so I can't say how good or bad they are. There's one called, I think it's called Go Debug. Yeah, there's one that Mailgun wrote called Go Debug, which apparently works. I've not tried it though, so I can't.
I was going to ask about concurrency. That's
Okay.
things that Go is supposed to be very good at.
Okay, we can talk about concurrency. So the first thing to remember with Go is concurrency. So Go has concurrency built in as a foundation of the language. The first thing to remember is that concurrency is not parallelism. So you hear that at every talk about concurrency. But having the appearance of doing more than one thing at once is not the same as doing two things at once. So for the most part, Go deals with concurrency and not with parallelism. So it will deal with the scheduling of doing two things at once and time slicing between them, but it doesn't necessarily deal with parallelism for you. Now the defaults have just changed in the new version of Go that's coming out, so that by default it does do parallelism for you as well, based on the number of cores your CPUs have. So let's look at Go routines. Okay, let's look at a simple one. That is a simple one, I think. So there's this keyword Go. And what that will do is start effectively a new, so it's not really a thread, but you can think of it as a thread. So it's a new computation that, you can think of it actually most usefully as a task if you're in C#, except it can't return anything. So if you imagine you had a task of unit if you're in F#, or a task of void if you could do that, then, or actually I think there's just a plain task which doesn't return anything that everybody advises against using. But a Go routine is like a task. And the way we can, okay, well let's just write a really simple one first, test.go. Func main, package main, import format. Function main, and then we'll do format println hello from main function. Okay, I spelled it twice the same way badly. Never mind, I'll just leave it. So let's say we had something that we wanted to do concurrently with this. So maybe we're writing a server, and we want it to continue accepting new connections and then spin off new tasks for every client that connects. That's a fairly common use case. This keyword Go we can use to invoke a function. So in this case, let's go and just write a function for it. It doesn't have to be declared in line, so we could do func say hello, and we'll pass in a string, so we'll say from string, and we'll just print out here format.printf. So this is the equivalent of using the format strings in most of .NET, and we'll say hello from s, and then we'll pass in the function, the thing there. Now this is going to format it badly for us. That's fine. It's just saying we have two mains in our package because I've got two files with a main in them, and that's fine. So in this case, we could run this function as a separate computation by saying go say hello, and then we'll say from a Go routine. And if we run this, then what we'll see is nothing happens. Why is that? Why is that? That does not look like what I was... Oh, it's probably because I didn't save it. No? Okay. What did I do wrong? Oh. I think I know what I did wrong. Okay. I'm going to ignore that example for a second and go back to the one that I know works, because I can't work out what's wrong with that very quickly. In this case, we've got one declared in line. So if we take away... Oh, actually, I do know what happened. We never waited on the function to complete, so the main function completed and then the program exited. Yeah, that's why we use this. So there's this concept of, there's a functional, well, not really a functional paradigm, but there's a model for concurrency called CSP, which Tony Hoare defined. And that's effectively concurrently running things that can only communicate between themselves by sending messages between them, down defined channels. So Go has channels built in. There's a type called chan something, where the something is the type that you want to send down it. So these things are typed, and they can be buffered as well. So you can have like a queue between different Go routines that are running concurrently. So in this case, we're going to send booleans down it, and this thing is going to be called done. So what's going to happen is we're going to do some work in our Go routine. In this case, we're going to mostly be sleeping. And then when we're done with our work, we're going to reply to the thing that kicked us off by sending a message down that channel. So note that we don't have a reference to the original thing which kicked us off. We just have a way of communicating with it. So we can say, when we define our function here, we can use this done channel, and we can send a message down it. The operator for sending a message is this arrow here. So we say, send true down towards done, and then whatever's listening to done will get it. The way you can read off them is very similar here. So you could put a variable name. If we wanted to know the value of that thing, then if we were going to send something other than true, then we could take out we could assign this to a variable like this. So we could say result like that. Actually, I think it would be an equals still. It would be that. And that would give us the value that we sent down. So you can use this for sending, you can send structures down it, you can send whatever you like down it, basically. And this operator blocks. So in this case, we're going to execute this in our main function. We're going to execute this. We're going to kick this off in a separate sort of background thread. We're going to print this message. And then we're going to block until we receive something from this other channel. So this is the equivalent of like waiting on a synchronization primitive. And then we're going to print this other message, and then we're going to exit. So this avoids the problem that we just had in the other demo where the thing exited before it actually had a chance to do any work. In this case, we're going to sleep for 2 seconds, then we're going to print a message from the Go routine, then we're going to sleep for another 2 seconds, and then we're going to say that we're done. So if we run this, then we get the one from the main function, we get the first one, we get the last one, and then we exit. So that's a quick introduction to channels. You can use these for sending whatever you like. So if we had a type, I don't know, type complex result struct, and then we had a int, b, int, c, int, or whatever, it's perfectly valid to declare a channel of complex result. This is in the same, it's not valid to send a boolean down it, but it's valid to declare. And at that point, we can use it similarly to a task in .NET, where we do some work. It will deal with scheduling it for you. It will deal with time slicing it for you. And then you can return this value by just sending a message down the channel. Of course, you're not limited to sending one message, so we could do this. Let's make this a channel of int and get rid of this structure, which we don't need. And we'll say we'll sleep for 1 second. We'll put a for loop in here that will run forever. So that's the equivalent of while true. And we'll say, well, actually we'll declare I equals 0, and we'll say I plus plus, and then we'll send it down the channel. Done. Oh, sorry. What was it? Done. I. And then here in the main thread, we'll just wait on that in another for loop, which will run forever. So we'll say result equals read from done, and then we'll print that result. So I think that should work. Let's try it. So what we'd expect to see is that this runs forever, printing a message every second as it gets sent down the channel. So you can use this for things like tick counters or whatever you need to. There's no guarantees as to the precise timing that they'll get scheduled, because obviously it's subject to some kind of thread scheduler, not only within Go, but also within the operating system as well. So there's no time guarantees here. But you can do a lot with just these primitives. So this is a good way of doing background workers, for example, without blocking the main threads. It's a good way of serving lots of different clients where you want to write the code in a sequential structure rather than with a ton of callbacks, but you want them to operate concurrently with each other. There's a thing you can set called, I think it's called Go Max Procs. I think it's, yeah, runtime Go max procs, and that will set how many processors it will try and use as an upper bound. So if you have, by default in Go, in the current versions of Go, this is set to 1 regardless of, what was it, procs? Yeah, by default it's set to 1 regardless of what kind of system you're running it on. In the new version of Go, it's set to the number of cores that you have available in total. So I think that's probably a more sensible default, but it may trip people up if they recompile their programs with that different setting. Who knows? So I guess we're kind of out of time. Are there any last questions? Or go for it.
You mentioned that there's no like real equivalence to DLLs, and the fact that like all the source you're using if you use a package is the source.
Yeah.
So is there no equivalent to like having a DLL out there?
No.
Like it has to be open source. The other one.
So as of now, the answer is yes.
Is obfuscate is that the only solution?
Wow, I'm not even sure that's a very good solution. As of now, the answer is yes, there's no way of doing a shared library. As of Go 1.5, I believe you can do it on Linux, and there is plans to extend that out to use DLLs on Windows and dilibs on Mac OS X. So I think that's coming, but it's not there yet. So yes, any code that you want to incorporate into a binary, which is all code you have to incorporate into a binary, has to be source available to you. There is a way that people do, there's a fairly common pattern at the moment of multi-part programs that talk over like a domain socket kind of thing as a pipeline. So that's the way most of the HashiCorp tools that, for example, Packer and Terraform, are all built so that they have plugins as separate binaries and they talk over a domain socket and sort of communicate in a similar way to Go routines do between them. Cool. Well, if anybody has further questions, then just come find me. I'm around, probably at the bar for most of the conference. So feel free. And thanks.